Okay, let's start. So today we will talk about the K-map, which is the algorithm to simplify the Boolean algebra equation, particularly to simplify the canonical forms. So in previous lecture, we talk about the sum of the product or sum of the midterm and product of the sum or product of the max terms. So basically, here in this slide, I use the midterm as one example. So we have already seen this example in the previous lecture. In this example, we have 3 variables, A, B, and C. So totally we have 2, 2, 3, 8. We have 8 rows here. And we have 2 output. One is F, the other one is G. So in order to have the sum of the midterm, we need to pick up of the rows which can generate a 1. For example, this row for F, this row, and this row. So totally we will write the sum of the midterm like this. So each row which can generate a 1 can be represented by 1 midterm. So the row 1, row 5, row 6, row 7 and midterm which can generate a 1. And we just need to sum them together. And we can use the same principle to write G like this. Although we have the canonical form, and by the canonical form, we need to guarantee that we have all 3 variables. All the variables need to appear in the canonical form, and we also need to enforce the order, alpha beta order, so that the computer can compare whether this canonical form equation is equivalent to another canonical form equation or not. So this is easier for the computer to do the comparison. However, if we directly use the circuit or the CMOS logic to implement the canonical form, we will waste a lot of hardware overhead, and we potentially will waste a lot of power overhead, power budget too. So in this way, we need a method or an algorithm to do the simplification. K-map is the algorithm which can be utilized by the computer to do the simplification. So here is one example. Again, K-map is also equivalent to the truth table, like the midterm, sum of the midterm of the product of the max term. So all these items are listed. K-map, truth table, sum of the product of the sum are equivalent, which means that you can convert anyone to another one among these items. So here is one example truth table. In this truth table, we have 2 variables, A and B. The output is called F. So we use ABC to represent the value of each row. So ABC can be 0, ABCD can be 0 or 1. And then we can convert this truth table to canonical form. So we write a table, a map like this. So this here is the A. So each column indicates one possibility of A. Either A is a 0 or 1. And here is the B. So each row indicates one possibility of a B. B can be 0 or 1. When A equals to 0, B is equals to 0. This is which is this row in the truth table. But in the K-map, we have this box. This box indicates what will happen when A is 0, B is 0, 2. So we use A to indicate the output here. The output can be 1 or 0. Then we write A, B, C, D like this. So you can check randomly, for example, this box. For this box, B is 1 and A is 0. Then we will go to this row. B is 1, A is 0, which is corresponding to the second row. So each box here indicates one row in the truth table. Then we just assign a group of value to the ABCD. For example, 0, 1, 1, 1. Then we write 0, 1, 1, 1 like this. And for this one, it's corresponded to the third row here, because here A is 1, B is 0, A is 1, B is 0. So they are equivalent. And then we can do the simplification on the K-map. How can we do that? We just need to group all the one together. We will draw some boxes to cover all the ones. Of course, there are some rules to draw the boxes here. For example, the box size has to be 2 to n. So either it's a 1, which is a 2 to 0, which is 1, or 2 to 1, which is a 2, or 2 to 2, which is a 4, or 2 to 3, which is a 8. So it has to be a 2 to n, some number of a 2 to n. If we have a 3 ones in this K-map, how can we handle that? Then we just need to draw 2 boxes. And of course, these 2 boxes can be overlapped. So when after we drawing the box, we finish the simplification, and then we can write the representations of this box. For example, this box. This box covered this. I'm sorry. This group covered this box and this box. So for this group, A is always 1, because for these 2 boxes, A is always 1. So we write A here like this. And B can be 0, B can be 1. So please recall that we have a law which is called B, or B bar equals to 1. So when we have a B bar and a B simultaneously, we just have a 1. So we use A multiply or and 1, which is still A. So this group can be represented by A. Then the final output of this Z is actually A. So by drawing some groups here, by grouping the ones in this K-map, we can do the simplification. And the group size has to be 2 to n. And one group may cover 2 to n boxes in the K-map. So if we have a 3, then we have to draw 2 groups. One group like this, the other group like this. Then we will write what each group represents independently. For example, for this vertical group, A is always 0. For these two boxes, A always 0. So we write A bar. B can be 1 and B can be 0. So we have no B because B or B bar is 1. So A bar multiply 1, which is still A bar. And then we write what this horizontal group represents. So for this horizontal group, for these two boxes, B is always 0. So we write B bar here. A can be 1 and 0. So A or A bar equals to 1. So we have a no A here. We write B bar here. And then we just need to sum these two groups together. All these two groups together. Sum here represents all. So you can see that by this way, in this way, we can do the simplification. Can we group 0 and 1 together? No. We can group all ones. We have to group all ones together, like this way. So group 1 and 0 together is not allowed. Can we draw a group like this in this way? No. We can draw a horizontal one or vertical one. So two boxes has to be horizontally connected or vertically connected. We cannot draw a diagonal line. So this is not allowed. So, but we can have some overlap. Like in this example, we have an overlap here. Can we draw a group covering 3 ones? No. It has to be a 2 to n. 2 is allowed. 4 is allowed. Can we draw a group like 5? No, because 5 is not a 2 to n number. So if we have this example, how can we do that? We can divide it into two groups. One group is a horizontal group. The other one is a vertical group. So these two groups have some overlap, which is this box. And we should draw as large group as possible. The group has to be as large as possible, and we should have the number of groups should be as small as possible. For example, we have 6 ones like this. Then we need to use a group to cover them as large as possible. This is one group, and this is another group. So by two groups, we can finish the simplification. Can we do this 3, like cover them by 3? No, you cannot. 3 is not possible. 3 is not allowed because you just do one extra group here. One extra group represents you will have an extra item in your final Boolean algebra equation. So that's not the simplest form of your Boolean equation. So that's the reason why we want to have less group as possible, have as large group as possible. So can we do something like this? We have one group. We have another group. So in this way, we also have 2 groups. This can be allowed. Why? Because we have the same number of groups. They do not have, the only difference is that whether you have overlap. So in this case, you don't have an overlap. But again, all the K-map like this is better than this one. Why? Because for this case, we have 3 variables, A, B, and C. So this horizontal group can be represented by C bar. Why? Because for all the 4 boxes here, C is always 0. So we write a C bar here. And we have all the possibility of A and B, 0, 0, 0, 1, 1, 1, 1, 0. So we have all the possibility of AB, so we do not have AB. What does all the possibility here mean? It means we use A bar and B bar plus A bar B plus AB plus A and B bar. So when we add these atoms together, the result is 1. So we do not have anything others here. Then if we draw the group like this, although we still have 2 groups here, but this small group can be represented again also C bar, because for these 2 boxes, C is always 0. Then for these 2 boxes, we have A. I'm sorry, we have A is always A is always 0, but B can be 0 and 1. So this group can be represented by the C bar and A bar. You can see that this part is more complex than the C bar only. Because in order to implement the C bar only, we just need a NOT gate. But here we need a 2 NOT gate and 1 AND gate. So you need to draw the group as large as possible. Although in these 2 cases, both cases have 2 groups, only have 2 groups. But again, even the two groups cases are different. You need to draw the one group as large as possible. Why? Because for a large group, you have a more simplified items. And I also would like to remind you a fact in this K-map. So for the C, we have 0 and 1. This is the same as the 2 variable case like this. B can be 0 and 1. C can be 0 and 1. But for here, for AB, we have a 0, 0, 0, 1, and then not 1, 0. It's a 1, 1, and 1, 0. Why we arrange the boxes like this? Because we want to guarantee that only 1 bit is flipped. If we jump from one box to its neighbor. For example, if we start from 0, 0, then we go to 0, 1. Only the second bit is flipped from 0 to 1. If we jump from 0, 0 to 1, 0, then only the first bit is flipped. So in this way, no matter we jump to here or jump to here, only 1 bit is flipped. So if we start from this column, if we go to this column, then only the first bit is flipped. However, if you change 1, 0 here, if you change this like 1, 0 to 1, 0, then both bits will be flipped. You cannot guarantee only 1 bit is flipped if we start from one cell and then jump to its neighbor cell. So each one has to be in one group. You cannot discard one. If you discard one box here, then the result will be incorrect. Group can be overlapped like this. So if you do not want to have overlapped group, then you will have more groups. More groups indicate a more complex result, which is not a simplified result. And groups may wrap around the table. So this column is actually the neighbor of this column. So they are actually connected. And this row is actually connected to this row. Then when you draw the K-map, you need to have as few groups as possible. So you can actually view the K-map like this. So the K-map can be wrapped up like this. So each cell is actually adjacent to 3 other cells. In this example, this is the 3 variable K-map. And also you need to be careful. This is 1, 0. This is 1, 1, not 1, 0. This is 0, 1. I'm sorry. This is 0, 1. This is 1, 1, not 1, 0. So here I write all the rules here. You can try them yourself. Here are the example of group 1, group of 1, group of 2 terms, group of 4 terms. Here are some examples. So the K-map can also help you to simplify one existing Boolean equations. For example, if you have an equation like this, then you just need to write each item into the K-map. For example, if the first item is A bar C, so this is a 0. This is 1. This is 2 zeros. This is 0, 1. This is 1, 1. Again, this is 1, 1, not 1, 0. The last one is a 1, 0. Since we have A bar C here, then A has to be 0. And C has to be 1. We have no other items, so B can be 0 and B can be 1. So we just, this item is actually equivalent to these 2 boxes. And this item is related to this box. And this item is related to these 2. Because for this item, B, we have a B and a C bar. B has to be 1. And C has to be 0. So which is this column. We have no A here. A can be 1, A can be 0. So this item is related to this box and this box. So after we draw the ones, all the ones here, we can do the grouping. And of course, we would like to group, the variables, the ones like this. Why we don't group this single one? by one group because we want to draw the group as large as possible. We can accept the fact that they have some overlaps, which is this one. Then you can rewrite the grouping result back to the Boolean equation. For example, for this 4, B is always 1. C can be 1, C can be 0. So we have no C. A can be 0, A can be 1. So we have a no 1. So so we only have a B. So this size 4 group is equivalent to B. And this group can be written as A bar C. Because for this row, A is always 0. So we have an A bar here. And then B can be 0, B can be 1. So we have a no B here. And then C is always 1. So we write C here. Then by drawing the K-map, we can not only simplify the canonical form, we can also simplify any Boolean equation here. So this is an example for canonical form. We just write it all at once and do the grouping. Do we need to draw a vertical group here? No, we don't. Why? Because these two ones has already been covered by some groups. And here is another example of the canonical form. We just write all the ones here and do the grouping. After we do the grouping, we can write the simplified items here. So here is one example. You can try them yourself. Before you try, I would like to remind you, okay, when you draw a 3 variable K-map, this is a 0, 1, and this is 1, 1, not 1, 0. So this is a very easy mistake. And then this is the 4 variable K-map structure. So you can see that this column is actually connected to this column. And this row is actually connected to this row. And now we have a 0, 1 to 1, 1, and we also have a 0, 1 to 1, 1. 0, 1 is always connected to 1, 1, not 1, 0. So you need to be careful when you handle the 4 variable case. You have a 1, 0, 1 to 1, 1. From the column perspective, you also have another 0, 1 to 1, 1 case from the row perspective. So only in this way you can have this structure. So 4 variable case is just larger. You have a larger table, but you need to follow the same rules to do the grouping. For example, if you do the grouping like on this K-map, you can draw the K-map like this. So these 2 columns are the easiest one. And this one is also can be understood because you don't want to only draw a circle or group cover this one. You need to have a overlap. The overlap can guarantee you have a more simplified version. But for these 2, you need to draw a group. You need to draw a group like this. These four ones are actually connected. If you draw a group only cover two of these two, then that's not the largest group you can draw, which indicated that that's not the most simplified version of this equation.
I have a question.
Yes.
So in here, well, in one of the previous slides, you showed that the map in this case would be kind of like topologically a cylinder. So it's
Yes.
more like this torus now when we're doing 4.
Yes.
Okay.
So why we have this structure? Because these two columns, the first column and the last column are actually connected. And the first row and the last row are actually connected. So this M0 is actually the neighbor of M8. M8 is the neighbor of M10. M0 is the neighbor of M2. So that's the reason why we can group them together. So totally we have a large vertical group, including composed of these two columns. And then this is the second group. And then this is the third group. Then we have 3 terms here. The largest one, this 8 boxes group can be written as a C. And then this small group can be written like this. And this 4 boxes group can be written like B bar and the D bar. So sometimes we have some don't care signal. Don't care signal can be 1 and 0, but not simultaneously. We can treat them as 1 or 0 because we do not care about their values. We use this symbol to indicate don't care. So when we have when we draw the K map with the don't care symbol, we can treat them like 1 or zeros. Again, by following the principle, if we treat them like 1, then we can have a larger group. Larger group indicate a more simplified equation. So in this case, we just treated these 3 as 1, but this one as 0. Then we have this result. We can also group these two together as one group. So they should have the same complexity because no matter you group these two together or these two together, we have 4 groups here. And no matter we have this group or this group, they should be the same because both groups are 2 boxes group. So the result can be this, like this, or this. They are very similar. Only one, input is different. But from the complexity perspective, they are the same. Which means that when you do the simplification, potentially you may have different answers, and both answers can be correct. Here is another example with the do not care input. So in order to draw a group as large as possible, we treat these two as 1, and these two as 1, but this as 0, and these two as 0. or we can draw the K-map like this. We can group these four together. I believe both cases are correct. Why? Because for this drawing, we have two 4-box groups. So this is one 4-box group, second one 4-box group. And for this drawing, we also have one 4-box group and another 4-box group. Do you need to draw a group like this? No, you do not. Why? Because you can treat all the do not care in this box as 0. So you do not need to have this item at all. So 2 groups are enough. So that's all. Any question? So by the K-map, the computer can have an algorithm or a method to simplify not only the canonical form, but also any Boolean equation. So you can write your Boolean equation into the as a K-map and then do the simplification. Eventually, you will have a simplified Boolean algebra. If no question, we can stop today. Thank you very much.